We shall now study a very interesting class of lattices called distributive lattices. In set theory, you might recall the following formulae. If you have three sets A, B, and C, then A intersection B union C is A intersection B union A intersection C. And dually, A union B intersection C is A union B intersection A union C. These are called distributive laws. And we can define a lattice to be distributive if the join and meet of this lattice satisfy these distributive laws. So A join, let's say A meet B join C is equal to A meet B join A meet C, and A join B meet C is A join B meet A join C. Now suppose, for example, your lattice consists of it's a subset of sets. It's a subset of the power set of subset, and closed under intersection and union. Then the join and meet of this lattice will coincide with the intersection and union of the sets. And so what we'll have is distributivity. For example, more specifically, if I take lambda to be Jp for some partially ordered set P, then we know that join and meet in Jp are just intersection and union. And hence, for example, we know that Young's lattice is a distributive lattice. Let's look at another example which isn't obviously of this kind. Take the poset of positive integers under divisibility. Now in this, M join N is the GCD of M and N, and M meet N is the LCM of M and N. And I claim that this lattice satisfies the distributivity laws. It's not immediately obvious, but an easy way to see this is to identify elements of P with subsets of some set. So I'll just define rho from P to the set of subsets of the natural numbers by defining rho of n to be the set of prime powers, elements of the form p to the power k, such that p is a prime, k is a positive integer, let's just say k belongs to p, and p to the power k divides n. Then you can show that M is divisible by N if and only if rho M is contained in rho N, and M join N is rho M intersection rho N. The prime powers dividing the GCD of two numbers are precisely those prime powers which divide both the numbers. And for LCM, you have rho M join N is rho M union rho M. And so the lattice of positive integers under the divisibility partial order form a distributive lattice. The lattices JP will play a very important role in the theory of distributive lattices. So let's try to understand a little bit better the relationship between a poset P and its lattice of ideals JP. So firstly, given any poset P, we can define a function J from P into Jp in a kind of obvious manner. J of x is just the ideal generated by x for every x in P. This is just the set of all y in P such that y is less than or equal to x. Such an ideal which is generated by a single element is called a principal ideal. Now the question is, what is the image of the function little j? Or maybe make it more precise, characterize Jp in terms of the lattice operations on J. The lattice structure on Jp. In order to answer this question, we need to make a definition. If lambda is a lattice, an element x belongs to lambda is said to be join-irreducible if firstly x is not the least element of our lattice, and secondly if x is y join j, then x equals y or x equals j, z. This is a bit like the definition of an irreducible polynomial. And the answer to our question comes from this definition. This is clearly a definition that is just dependent on the lattice structure of the lattice. And the theorem is that Jp is the set of join irreducible elements of Jp. Let's prove this. So firstly, I want to show that every principal ideal is join irreducible. So suppose that I have a principal ideal Ix, and this is of the form I1 union I2. Now x lies in Ix, so x must either lie in I1 or x must lie in I2. But if x lies in I1, then I1 is equal to Ix because it's an ideal containing x that's contained in Ix, so it must be equal to Ix. And if I is in I2, then I2 is equal to Ix. So this means that Ix is in fact, well, it's clearly non-empty because it contains x, so is join irreducible. For the converse, let's suppose that I is not a principal ideal. So it does not belong to Jp, i.e. it's not a principal ideal. Now the smallest set that generates any ideal is the set max I, the set of maximal elements of I. And since I is not principal, this set must have more than one element. So then I would be able to write max I as a disjoint union of two non-empty sets. Any set with more than two elements can be written as a disjoint union of two non-empty sets. And now I have I is equal to the ideal generated by S union the ideal generated by T. I is generated by S union T. And both these are proper ideals because S and T are proper subsets of max I. So IS will not contain the elements of T and IT will not contain the elements of S. So I is not equal to IS and I is not equal to IT, which means that I is not join irreducible. And so that proves the theorem. We are now ready to state the most important theorem of this lecture, namely the fundamental theorem of finite distributive lattices. This is a structure theorem for finite distributive lattices, or in some sense it reduces the classification of finite distributive lattices to the classification of posets themselves. And this theorem is due to Birkhoff. And the theorem says that every finite distributive lattice lambda is isomorphic to the lattice of ideals of P, where P is the induced subposet of lambda consisting of join irreducible elements. This is certainly suggested by our earlier calculation, where we saw that the P sits inside JP as join irreducible elements. And so if lambda were isomorphic to JP, then P would have to be the join irreducible elements of lambda. So if you know that every finite distributive lattice is isomorphic to JP for some P, then this point that P is consists of join irreducible elements is forced. So let's prove this. And to prove this, we'll try to define a function from lambda to JP. And given any element x in x, we'll define this to be the ideal consisting of all y in P such that y is less than or equal to x. So these are all the join irreducible elements that are less than or equal to x. Here x need not be in P. X is a general element of lambda. And so this inequality here is actually in L. But of course P is an induced subposet, so inequality in P is the same as inequality in L. We don't need to write this symbol, but I'm just signifying here that x is not even in P, so it's in L. And this of course is an ideal, because if y prime is less than or equal to y and y is less than or equal to x, then y prime is less than or equal to x. So phi x is an ideal, and so this is a well-defined map from lambda to JP. And it's also order preserving, means that of course if x is less than or equal to y, then phi x is less than or equal to phi y, because if any element is less than or equal to x, it's also less than or equal to y, because x is less than or equal to y. So this is obvious. The next point is that phi is injective. So to show that phi is injective, I just need to show that x can be recovered from phi x. Now to do this, I'll need a little trick, and maybe I'll state it as a lemma. So lambda, remember, is a finite distributive lattice, every element under that hypothesis, every x in lambda can be expressed as x equals x1 join xk, where x1, xk are join irreducible. So one thing that you need to be careful here, if x is actually the least element of the lattice lambda, then x is just the join of the empty set. The empty join is taken to be the least, well, it's the least upper bound of the empty set, and so it's going to be the least element of your lattice. And so this is clearly true with k equals 0 for the least element of lambda. But for any other element, what you can do is, I'll just give you an idea of how to prove this. So if x is already join irreducible, then we're done. But if x is not join irreducible, what you can do is you can write x as x1 join x2, where x1 and x2 are both strictly less than x. Okay. And now if x1 and x2 are both join irreducible, then you're done. If not, say x1 is not join irreducible, then you can write it as x11 join x12 join x2, where x11 is strictly less than x1, x12 is strictly less than x1, and of course x2 and x1 are strictly less than x. And you can carry on this process of each time you have a certain decomposition, if any of the elements in that decomposition is not join irreducible, then you can further split it into the join of two elements that are strictly smaller than that element. Now, because lambda is finite, this process cannot continue forever, because if you do this process n times, you'll have a strict chain of n elements in your poset. And so that process must stop at some point. And so that's why every element in a finite lattice can be written as a join of join irreducible elements. Okay, so I'll let you think about the details of that proof if you feel you need more convincing. Now this will let us recover x from phi x. And the key to recovering x from phi x is to just take the join of all the elements of phi x. And this will imply that phi is injective, because I have shown you how to recover phi from phi x. So let's just prove this. So let's start with the right hand side. This join. Well, now suppose x is of the form x1 join x2 join xk, then each of those xi's is less than or equal to x, and therefore it is an element of phi x. So in this join, we already have the elements x1 join x2 join xk, and then we have other elements y which are not in these. But there's no harm in again just writing y belongs to phi x, because if we write any element twice, xi join xi is still xi. So if I just write an element twice in the join, it's not really going to change the join. So I just write it like this. So it's x1 join x2 join xk, and then the whole thing join this thing that we started off with. But now that is the same as x join y in phi x y. But each element in phi x is already less than or equal to x. So if I take x and join an element that's less than or equal to x, I'm still going to get x. And if I keep doing that repeatedly, I'll keep getting x. So this is equal to x as claimed. And so what we see is that x can be recovered from phi x, and so phi is injective. So we've proved that we've constructed an order preserving function from lambda to jp. And we've shown that it's injective. We haven't at all used the fact that lambda is a distributive lattice. And it's only for the surjectivity that we need that lambda is distributive. So what I want to show you is that every ideal comes from is phi x for some x. So take I in JP, and then the previous proof suggests that I want I to be phi x, suggests that I should take x to be just the join of all the elements in I. Now, of course, we know that I is contained in phi x, because if we have any element in I, then x is the join of all these elements. So x is greater than or equal to y. So y is in phi x. Okay, so that's easy. So for the converse, let's start with any element u in phi x. So u is less than or equal to x. Then I can write u as u join x. This is in fact equivalent to saying that u is less than or equal to x. Which now, what was x? X is this join, so I can write this as x join, x meet the join of y in I, y. And now I can use distributivity to write this as the join of y in I, x meet y. So I've used distributivity for an intersection with the join of multiple terms, whereas I stated distributivity only for the join of two terms. But it's not difficult to see that these are equivalent as long as I have a finite join over here. You can prove that using induction if you wish. So what happened is that u has become, this is a u join meet x. So u has become a finite join, and join irreducibility, again, I stated it only for two elements, but it's true that if you have a join of any number of elements, if an element is join irreducible, it must be equal to one of those. Again, you can prove that by induction. So by the join irreducibility of u, we must have u is equal to u join y for some y in I, which means that u is less than or equal to y for some y in I, which implies that u itself belongs to I because I is an ideal, and so if y is in I and u is less than or equal to y, then u is in I. And so this shows that phi x is contained in I. And this completes the proof of surjectivity and hence the proof of the fundamental theorem of finite distributive lattices. This theorem has several interesting corollaries. The most obvious being that for any posets P and Q, of course, if P is isomorphic to Q, then JP is isomorphic to JQ. Just the isomorphism from P to Q carries over to an isomorphism of ideals, but the converse is also true, because if these two lattices are isomorphic, then I can recover P and Q as their induced subposets of join irreducible elements. Here's another very interesting corollary. So before I get to that, let me just define the dual notion of join irreducible. Let lambda be a lattice. An element x belongs to lambda is said to be meet irreducible And you can very well guess, if x is not equal to the largest element of the lattice, and if I write x as y meets z, then x is equal to y or x is equal to z. So it's a dual notion of join irreducible, in the sense that the meet irreducible elements of the opposite of the lattice lambda are the join irreducible elements of the lattice lambda. It's just the notion obtained by reversing the signs in the partially ordered set. And here's a very surprising corollary. If lambda is a finite distributive lattice, then its subsets P consisting of join irreducible elements as before, and Q consisting of meet irreducible elements, these are actually isomorphic. So let me just give you a quick proof of this. So firstly, note that the opposite of lambda, this is the lattice of ideals in the meet irreducible elements in lambda are the same as the join irreducible elements in lambda op. So these become the join irreducible elements of lambda op. And of course, I must take the reverse partial order. And so lambda op, by the fundamental theorem for finite distributive lattices, is J of Q op. Now, the function which takes I to Q minus I is an isomorphism. From J of Q op to JQ. Okay, you can easily check this, and therefore what we have is that lambda, which is isomorphic to JQ, is isomorphic. Now this taking this, right, this is again by the fundamental theorem of finite distributive lattices, and here we have lambda op is isomorphic to JQ op, which means that again, lambda is isomorphic to JP by the fundamental theorem of finite distributive lattices, and here what we've shown is that lambda op is isomorphic to JQ op, which means that lambda is isomorphic to JQ, which implies that P is isomorphic to Q by the corollary that we stated earlier, that if JP is isomorphic to JQ, then P is isomorphic to Q. Here's another interesting corollary of the fundamental theorem. Let lambda be a finite distributive lattice then we already know that every element of lambda can be written as a meet of meet irreducible elements, but this representation is unique. Then every x belongs to lambda can be uniquely written as x equals x1 meet x2 meet xk, but we need to discard some very obvious ways of getting redundancies. If we have x1 and x2 and x1 is less than or equal to x2, then x1 meet x2 will just be x2. So we don't want these. So we'd say where x1, x2, xk form an anti-chain. This is an irredundant expression of x as a meet of finitely many elements. And one way to understand this is to just say that suppose phi of x, this is in Jp where p is the set of join-irreducible elements of x, has max phi. So phi x is in Jp and max phi x. So what I want to say is suppose max phi x is equal to x1 xk, then x is equal to x1 join xk. This is going to be an anti-chain, and this characterizes the expression of x as a join of k join irreducible elements, because x is anyway already recovered by y belongs to phi x y, and I can just take the maximal elements and it will still be the same thing. And conversely, if I write x where these form an anti-chain, then phi x, because of the lattice isomorphism, phi x is phi x1 join phi xk, which means that each of these xi's is a maximal element of phi x. And so the decomposition has to be this one. I will conclude by pointing out that through the fundamental theorem for finite distributive lattices, we also have a method for computing the Mobius function in distributive lattices, and not necessarily just finite ones. Let's take, for example, Young's lattice. So remember, Young's lattice is J of p squared, and we have this is not a finite distributive lattice, but it is a distributive lattice. Let us try, for example, to compute the Mobius function at two values. Let's say take the partition 2, 1, 1, which is certainly contained in the partition 3, 2, 2. Now this interval 2, 1, 1, comma 3, 2, 2, it is a subposet of distributive lattice, and in fact it is closed under meet and join, because if you take the meet and join of two elements in interval, they still are they lie in that interval. And so this is actually a finite distributive lattice. And so we can try to compute the Mobius function by realizing this as the lattice of order ideals in some of finite distributive lattice. Recall we'd shown in an earlier lecture that mu jp of I comma j is, firstly, it's 0 if unless j minus I is an anti-chain. So let's write it like this. It's minus 1 raised to the size of j minus I if j minus I is an anti-chain, and it's 0 otherwise. So now let's just try to draw 3, 2, 2 and 2, 1, 1 as ideals. So let's first draw n squared. So n squared is a grid like this. Since it's a Hasse diagram, I'm tilting the grid so that the order relations are properly reflected. And 322 is given by this order ideal 3, 2, 2. And 211 is a subset, and it's given by this. And what you see here is that 322 minus 211 is certainly not an anti-chain, because there are these two nodes which are related. And so this here must be equal to 0. Let me just do another one for you which will not work out to 0. So let's say 221, 322. And here now we have a new node in 221. But what you see is that the difference here is in fact an anti-chain, just consists of these 2 points. And so this will be equal to 1. Strictly speaking, I haven't been working in an interval here, but I've been working in a slightly larger finite distributive lattice, say the lattice of integer partitions which fit inside, let's say, a rectangle like this. It's a square. That's still a finite distributive lattice. And so these calculations all work out. So the fundamental theorem of finite distributive lattices actually tells you how to compute the Mobius function for any finite distributive lattice. You need to realize the finite distributive lattice as JP, and then in JP you can use this formula to compute the Mobius function. And in the theorem, the construction of P is also kind of algorithmic, in the sense you can just check if each element is join irreducible or not, and thus identify P as a subset of lambda.